Hello, I've had a question in Unit 4, Lesson 6. Looking at number 6, it says a box with an open top is to be constructed from a square piece of cardboard 3 meters wide. So it's square, so that means each of these sides are of equal length. So it's a 3 by 3 square. We're cutting the square out of each corner. So that means I'm going to cut X out of each of those. So I guess this will be double hashes. Doubles, doubles. All right. And we're going to fold it up. So find the largest volume you can have. So my optimization equation is a volume, length, width, and height. All right. So the constraint equation. What will our constraint equation be? It'll be surface area, perhaps. So we know that the amount of cardboard okay, this one's a little funny. Sorry, I'm going to back it up. The constraint equation is how much we cut out of the corner. It's how big X will be. So for example, if we look at, let's call this the width, our width will be 3 meters minus 2 X's, because we're going to cut an X here and an X here. So the reason it's a constraint equation is because we don't know how much we're cutting out. Similarly, if I look at the length, length is also 3 meters minus 2x. So that's our constraint equation in that direction. And finally, our height, it depends how much I'm going to cut out to create the height of the box. So height equals x. So this is a unique one because we actually end up with 3 constraint equations to head into the volume. So volume equals length, width, and height. So 3 minus 2x, 3 minus 2x, and x. So that would mean I'm going to put the x out front. That's going to be 9 minus 12x plus 4x squared. So my volume is 9x minus 12x squared plus 4x cubed. Now we're going to optimize. So we're looking at the change in volume with respect to the height that we're cutting. So 9 minus 24x plus 12x squared. We let change in volume with respect to the width equals 0. 0 equals, and I look at that, I can pull a 3 out. So it leaves me a 3 minus 8x plus 4x squared. So at this point you have a choice of factoring or using quadratic formula. I'm just going to jump to the quadratic formula. Negative 8 squared minus 4 times 4 times 3 over 2a. So using our calculator, we get 8 minus, so it'd be 64 underneath there, minus bracket 4 times 3 equals, so that'll be plus or minus 4 over 8, which would mean we have 12 over 8, which is 1.5, or 1.5, or 8 take away 4 is 4 over 8, so 1/2. So therefore, there are 2 possible solutions here to optimize our volume, and they would be, so therefore, there are 2 options. So we could have a 2 times 1.5. Well, if we use this is kind of funny here. When you go to check, so let's say the width from up here says 3 minus 2x. So if we plug 1.5 in here, 1.5, that's equal to 0. So that is minimizing the volume completely. Obviously, this is inadmissible then if that's the case. So if one of your solutions gives you inadmissible, if it gives you an answer that doesn't make sense, it means that it's inadmissible. So that means there's only one possible option, and that is a box that's 1/2 by 1 by 1 meters in dimensions. All right. If you have any questions with that, and you'll find this whenever you get a quadratic like we did up here, there may be 2 solutions, but with optimization, often it's usually one of them because one's inadmissible. So if you have any questions with that, let me know.